So hello, good evening and welcome to Copper Junction. What's this program all about? Well, it's about cloud monitoring. And for those of you that don't know what cloud monitoring is, it's not really about looking at clouds. It's about the Internet of Things. And if anybody knows anything about the Internet of Things, it's a new up and coming fashion. It's true, it is an up and coming fashion, and a lot of people now are using that facility in order to do some dynamic watching of sensors and apparatus that can be connected to the internet. So this channel is about the use of some of those devices and how we can best design them and how we can best use them. Now this is a deep dive really, so this channel is primarily aimed at people who have a technical background and are looking to find out some more information, or to at least watch someone else carry out some tests and some theories on how best to do things on the connectivity front. Now we will be using a particular device in the first part of this series anyway, that's made by Capacitive. It's a 32-bit wireless device, and we're going to use that in its own enclosure to actually connect to the internet. Now there are numerous programs out there in order to make this work that are driven by Arduino. So check out Arduino. It's got lots and lots of information there about using these devices. In actual fact, I have a device here that we will in fact be using, and it is the Capacitive device. So you can pick these off the internet. They are pretty cheap. We're talking $5 to $10 as a max. They are very user-friendly, in terms of programming. As I say, lots of libraries, lots of things you can do. So in this particular series, or this particular video, I'm going to concentrate on a particular problem, which is water monitoring. Now, water monitoring is a subject in its own right. There have been many articles written on it. There's been many items published on the net. Go out and have a look at those. There's lots of different ideas about how to measure water in terms of its level or its height, and some very good articles. So in order to use this particular device, we're going to couple this up to a monitoring device or a monitoring enclosure where we can mount sensors and actually keep an eye out for any variations on particular parameters associated with the water. In actual fact, we're going to use this for monitoring a pond, a koi pond in fact. So what I want to do is to test this by monitoring the water level, by monitoring the temperature of the water, the ambient temperature, and most importantly of all, the pH of the water, which is obviously key to a lot of people who want to be able to keep an eye on what their water is up to. So I'm going to explain some of those devices. I'm going to get into a block diagram in a minute to show you how we could possibly realise that using what we have at home, which is obviously our home router, and how we couple it up to the net and how we can watch certain things. So we've got the sensor station itself, which is effectively a driver section to drive the I2C, and we've then got the individual components inside or on the board which will be collecting the information. So one of those key ones is the depth charge capacitive sensor, which is our capacitive frequency changer, which I will describe in a bit more detail with the schematic diagram to show where that is. There is a separate section on this itself, which I will go into. There is on the board an ambient temperature sensor. When I say it's on the board, it actually is a tiny small daughter board which I've put together that will be bolted to the side of the enclosure itself, and there'll be a copper wire to the outside weld just to gather the ambient. The water temperature itself, I've mounted the chip directly on the board, the main board, and more about that later in the schematic, and along with the daughter board, which is our pH level sensing, which I'll describe in a bit more detail in a minute. So I mentioned previously that the first interface connectivity to it was via the I2C driver, which can drive quite long lengths of copper, reasonably long lengths, probably as much as 30 or 40 meters of cable, which the I2C bus normally can't put up with that. It was originally a fillet specification, which was for obviously internal routing of data within things like television chassis and that kind of stuff, and to try and use it externally is difficult at best because of the touchiness of the rise time of the specification itself. It wasn't designed to be put up, transferred across large amounts of capacitive type cables, because the rise time then is completely and utterly ruined. However, using the driver chip and being a bit careful about how you're driving the wire, we can have 12 volts on the actual driver itself, and then use the other side of the driver, can be as much as down as much as to 3.3 volts or even 5 volts. But in my case, I'm going to opt for the 5 volt rail, because the chips internally are 5 volts. The other side of it, where we interface to the expressive chip, is 3.3. So the other side of the complementary chip on the other main board, the other enclosure, as I say, will in fact be 3.3. So this is a bit of a conversion chip as well as. So following it through, we've got the A to D converter, which is straight after the I2C serial driver, and so the serial driver will be communicating with directly with, using I2C, the A to D converter, and we've got 4 channels on the A to D converter, so effectively we can interface with 4 separate internals in order to get them out of the unit. In our case, I'm using a couple of temperature ICs, as mentioned previously. They're 2 I2C addressable chips, and more about those later, and we'll get some pictures of those and you can see them. We've then got the pH sensor. Again, I've mentioned it previously, but it's all analog, in the analog domain, and we get a swing between 0 and 5 volts depending on the pH of the actual outside water or the pond water itself. The capacitive wire sensor actually interfaces to an astable multi-vibrator. We're using a 555 for this, so it's going to be running in astable or free run mode, but of course the frequency of it will be modified by the capacitance, in that instantaneous capacitance that's on the on our sensor itself. Again, I've got a separate section on this as well as that should be coming up, that describes that in a bit more detail, so that you can understand how that interfaces to it, and perhaps some of the calculations associated with trying to get some capacitive value which will make sense with the frequency. So we'd like to set the frequency at mid-rail somewhere around about the 4 to 5 kilohertz region. We can do that if we can find the right capacitance for a piece of enamel copper wire of the right length, and I'll talk more about that in a minute. From the multivibrator, we feed this to a frequency to voltage converter, which again enters another input on the HDD converter, which is our 16-bit converter. Now, for a lot of this stuff, people have in the past used the actual HDD converter that's on the expressive chip. Now, it's not a bad A to D converter that sits on there, but its accuracy is not particularly brilliant. So this is why the decision was taken to off-board that one and actually put it in the head itself. So let's look at what we could use in order to create this capacitor that can measure water depth, and what its construction might be. But first of all, we need to go through some of the ideas and principles of creating a variable capacitor that can be modified by water level. So let's just look at some of the equations that we might have to consider when we're designing or thinking about designing something which is going to be a variable capacitor of some description. Of course, we've got our old usual empirical formulas for capacitance that we know and love. Obviously our famous mu naught mu r A over D, which of course, as we know, is mu naught being our relative permittivity of free space, you R being the relative permittivity of the material that we'll be separating the plates of the capacitor, and A being the area of the plate, or the plate area of the capacitor itself, and D being the spacing between the plates. So as always, D is very much related, inversely proportional to, should I say, the capacitance, and the smaller therefore the distance, then of course the greater the capacitance. So how do we measure the capacitance of a single piece of enamel copper wire? Obviously from the formulas on pure capacitance, they're not going to hold any water, if you pardon the pun. So what we're going to need to do is to look for another equation, and I've managed to find one that's an interesting equation which was used for to measure the real-time thickness of enamel copper wire, of the varnish itself as it's being applied to the solid wire. So the actual formula they used was 0.55 multiplied by relative permittivity multiplied by the length over log nat 1 plus 2V over D1, and it gave you in picofarads if you had the length being in centimetres. Now the centimetre length in this particular case is going to be 2 times L that we have here, because we did say that the wire would be run down internally inside of the tube, and therefore is going to be 2 times L as far as the actual overall length is concerned. We have to do this because we can't have an open end in the water for obvious reasons, and in fact we'll short it out through the water, through the resistance being so low through the water. So the water itself, relative permittivity, is around about 80. So coupled with the relative permittivity of the varnish, we should see some marked changes in capacitance if we use it in that way. However, let's just quickly work out how we're going to extrapolate the figures that we need to put into this equation. So we already know E because it's 4. The length we've already said is 2 times L. The 2V-D1 ratio is very quickly found out from subtracting D1 from D2, and that is equal to 2V. Now, V being these distances here of the varnish itself. Now those figures we can get, or that ratio we can get from the standard wire tables. So for us we're going to be using a standard gauge of 22, so from that we can work out what the figure of capacitance is going to be. Now as it turns out, when we put these numbers in, it comes out that in terms of picofarad for a length of wire that's effectively 2 times 300 in this case, or 2 times 200 if it's slightly smaller. If you work that out, it comes out to something in the region of around about 400 to 500 picofarad for that length, which is not a bad amount of capacitance given the way that we're creating it. Now remember that the reason this works is because of the incredibly small amount of covering of the enamel wire, which probably can work in your favour, and it may work against you if it's got pinholes in it or something along those lines. Now generally speaking, I think the manufacturing process in this day and age is pretty good, so it's unlikely you're going to get any of that, but of course if you have a failure, then it's possible that may be the cause. And obviously from a longevity point of view, how it holds up in water for a prolonged amount of time, I'm not sure, and it's something else that needs to be tested. But essentially, once we have our capacitance, we can put that into our standard or stable equation to get to some value of oscillation that it will come to. So if we do that, and in the stable running configuration of the 555, we could say that the frequency will be, the period will be 1.4 times R times C. R we've chosen in this case to be 150k. Now there's a reason for doing that, and that is a question of finding some frequency ranges which would be sensible. So in this case our C we already know as a bare bones C. Now when we plumb that into the equation, we find out that in the region of 400 to 500 puff, we're going to end up with a frequency of around about 9 or 10k. That's where we want to get to. So on the lower edge of it, when we have water halfway up the tube at about 150 millimeters, we want it to be sitting around about 3 or 4 kilohertz. That's an ideal situation. So first thing we've got to do is build it and test it, and that's the next stage we'll be moving on to. So we've discussed the theory behind some of these capacitive measurements and how we could possibly do it. So how do we put that into practice? How do we use materials that we have to create this adjustable capacitance? Well, one of the theories that we're going to try out is to use a short length of aluminium tube. You can see it here. This is 300 millimeters in length. This will be our outer tube and will be the tube that's grounded, effectively working with our stable 555 timer that's mounted on the board, and this will be the outer chamber. What we will do then is to insert in the middle of the chamber and actually thread wire down the outside of a piece of copper tube, which is an insulated bit of copper tube, just to use as a carrier for the wire. So if we look at the animation now, you can see that construction and how that's made up and put together. So in reality, what does it look like? Well, in that old cliche, as they say, here's one I made earlier. So here's my metal tube. It was originally painted black. I've made a 3D mount point. I drew this in CAD, and I've got the 3D printer to make up the moulding. It's also I've made up some other spacer elements which I've attached to the plastic pipe, and I've actually laced down on the outside of it a piece of copper wire, which is enamel copper wire for the insulation properties. And what I've done is I've threaded it down from the top, down through the spacers. I've just secured it with some tape on the outside, and actually it runs then as a loop through it and back up and out again. Now the reason for doing that is, of course, if I used a piece of solid, a single piece of wire, and it was open at the bottom, then I've got resistance to worry about through any form of water contamination. As it is, enamel copper wire is always a bit hit and miss, because there may be tiny little pinholes in the insulation which will completely and utterly ruin your idea of creating a capacitor. But let's see what happens. So here is my metal box. I've drilled some holes already in it. It's got a 30mm diameter hole, which is the exact size of my aluminium tube. So I've got a 30mm aluminium tube, which I've already said was 300mm long, and that will drop down with my pre-made mounting point to mount inside the box itself. So here we have the actual depth sensing enclosure. The board, the actual PCB board, will drop over the top of this, and the connections for the wires will connect directly to it.